Hello everyone, in this video we are going to discuss about counters. Counter is nothing but an electronic circuit that is used to count the number of clock pulses that arrives at the circuit. The counter is used to count the number of pulses. The number of pulses can be counted using the output of the counter. The output of the counter is nothing but the number of clock pulses. Counter is used in widest applications of the flip-flop. Counters are generally constructed using flip-flops. There are two types of counters, namely asynchronous counter and synchronous counter. In case of asynchronous counter, the clock signal applied to different elements of the counter are not same. Different elements of the counter will have different clock signals. Whereas in case of synchronous counter, all the elements of the counter will receive the global clock signal. In case of synchronous counter, all the elements of counters will receive the global clock signal. This is the truth table that represents the counter. Initially, the output of both the flip-flop, generally counters are constructed using flip-flop. Initially, the output of flip-flops will be 0 0, which represents the decimal count 0. When the first clock, this is how the clock signal will be represented. This is the positive rising edge. This is the falling edge. Generally, there are two types of flip-flops called positive edge-triggered flip-flop and negative edge-triggered flip-flop. When in case of positive edge-triggered flip-flop, the clock count will be increased to 1 when this phase of clock signal is applied. In case of negative edge triggered flip flop, the count will be increased when this phase of the clock signal is applied. When the first clock signal arrives at the flip flop, the output of both the flip flop will be changed to 0 1, which represents the decimal count 1. When the second clock signal arrives, the count will be changed to 1 0, whose decimal is equivalent to 2. When the third clock signal arrives at the flip flop, the counter output will be changed to 1 1, whose decimal equivalent is 3. When the fourth clock signal arrives, it will get into the state called 0 0, whose state is 4. We in this, using two flip flop, we could count 4 decimal counts. 2 power n counts could be counted using n number of flip flop. Here we are using 2 flip flop, so 2 power 2 is 4. We could calculate 4 counts of clocks. First, let's discuss about the asynchronous counter. Asynchronous counter is also called as ripple carry counter. In this video, we are going to see how to design asynchronous or ripple counter using T flip-flop and JK flip-flop. We could see that the first element of the counter, that is flip-flop A, is having the global clock signal, whereas the flip-flop B is not having the global clock signal. The clock signal applied for the flip-flop B is nothing but the output of flip-flop A. This is called as asynchronous carry ripple counter. Similarly, using JK flip-flop also, ripple counter could be constructed by setting both the inputs J and K as 1. In this case of JK flip-flop, both the inputs J and K has to be 1, whereas in case of T flip-flop, there is only one input T which is set to 1. This is set because when in T flip-flop, when the value of T is 1 and the clock signal is applied, the output is nothing but the toggled version of the previous output. When the value of T is equal to 1 and when the clock signal applied arrives at the T flip-flop, the present output is nothing but the toggled version of the previous output. Similarly, in case of JK flip-flop, when both the values of J and K are 1, when the clock signal arrives at the flip-flop, the present output is nothing but the toggled version of the previous output. The first condition is initially both the outputs of the flip-flop are 0 0. Initially both the output of the flip-flop are 0, 0, QA and QB are 0, which represents the decimal count 0. When the clock signal arrives, consider these two flip-flop or negative edge-triggered flip-flop. These are the negative edges. This is the clock signal and these are the negative edges. When the negative edge arrives at the flip-flop A, whose output is QA, when the negative edge arrives at the flip-flop A, the negative edge arises at the flip-flop A, the output gets toggled. Since the value of TA is 1, the present output is nothing but the toggled version of the previous output. So the output gets toggled. 0 is toggled to 1. So the value of QA becomes 1. This 1 is applied to the next flip-flop B. The 1 is considered as the positive edge of the clock. So there won't be any change in the output. So the state will be 1, 0, whose decimal value 1, 0, which in the sense 0, 1, whose decimal count is 1. During the next negative edge of the clock, this 1 is toggled to 0. This value 1 is toggled to 0 in the QA port. So the output of the first flip-flop is 0, which is applied to the clocks, which is applied as the clock signal for the second flip-flop. This 0 is considered as the negative edge of the clock. So this toggles the previous output of QB. The previous output is 0, which is toggled to 1, which in the sense 1, 0, whose decimal count is 2. 1, 0, whose decimal count is 2. During third negative clock edge, this 0, the output of the first flip-flop, 0 is toggled to 1. This 1 is applied as a clock signal to flip-flop B. Since 1 is considered as the positive edge trigger, there will be no change in the output of flip-flop B, which is 1. So this state is represented as 1, 1, whose decimal count is 3. So we have counted 4 states, 0, 1, 2, 3. The total number of states that are counted is 4. Thus, we have designed a counter that could count 4 clock pulses that arrives at its flip-flop. Next one is synchronous counter. The disadvantages of asynchronous counter is the clock signal applied to the second element is nothing but the output of the previous element. Since it requires the output of the previous element, there occurs a counting delay. It creates the counting delay, and propagation delay also occurs at the counting stage. The counters are connected like a chain. The drawback of this system is it creates counting delay. To overcome this counting delay and propagation delay, synchronous counter is used. To overcome the drawback, synchronous counter is used. In case of synchronous counter, both the elements have the same clock called the global clock. This global clock signal is applied to both the flip-flop. In this case, the first flip-flop will have the input J and K as 1, whereas in the second flip-flop, the input of the second flip-flop J and K is nothing but the output of the previous flip-flop. JB and KB is equal to the output of the previous flip-flop called QA. The same clock pulse is passed to the clock input of all the flip-flop. The clock signal produced by the flip-flop are same as each other. Both the flip-flop has the same clock signal. So the first flip-flop will work as a toggle flip-flop. Since both the input of J and K flip-flop are 1, this is similar to the T flip-flop. This JK flip-flop acts as a toggle flip-flop. Initially, both the output of two flip-flops are 0, 0, 0, which represents the decimal count 0. When the first negative edge clock passes to the flip-flop, since it's a negative edge triggered flip-flop, when the negative edge of the clock arrives, the output changes. When the negative edge of the clock when passed to both the flip-flop, since the input for first flip-flop is 1, it acts as a toggle flip-flop and toggles the previous output 0 to 1. When the clock signal is applied to this flip-flop, this 0 appears across JB and KB. The clock signal of the first flip-flop and both of its input will be set to 0. Since it is 0, this JB and KB values are 0, the output is also 0. The state is called as 0, 1, whose decimal equivalent is 1. When the whose decimal equivalent is 1. When the next negative edge arrives at the flip-flop, this 1 is toggled to 0. But at the time of clock arrives at this flip-flop, this 1 will be here. Since 1 is applied to J and K, this flip-flop will act as a toggle flip-flop and this value 0 will be converted to 1, whose state is 1, 0, whose decimal equivalent is 2. When the next negative edge arrives at the flip-flop, this 0 is toggled to 1, and when the clock arrives at this flip-flop B, this 0 will appear across J and K. Since J and K are 0, the previous output is maintained, which is nothing but 1, 1. So the decimal equivalent of 1, 1 is 3. Thus, using two flip-flops, we have designed a counter that counts 4 states. From 0 to 3, there are 4 states. 4 state count. The count value of this counter is 4. Thus, we have discussed the basics of both the synchronous and asynchronous counter. We could design these counter for any number of states. Using two flip-flop, we have designed a counter that counts 4 states. We could count any number of states by adding equivalent number of flip-flops. Thank you.